Hello, Met 232 class. The lecture today is about failure, Chapter 8. We began this topic in the last class period, looking at food or pharmaceutical packaging in this case, where we've got a pre-designed flaw in the packaging that when you load it under shear will ideally open the package. And we'll see again and again that a pre-existing failure can initiate, a pre-existing flaw can initiate failure, sometimes in this case desirable, but in most cases undesirable. Here the package when loaded in shear should open at that stress concentrator. This is fairly common in pharmaceutical packaging, obviously, but also food packaging. For example, if you've got an aluminum or steel bottle top that loaded under compression and then torsion will peel off and break the seal, for example, on a pop bottle. So those are design failures, but in most cases, the failure is undesirable. Here's the classic case of a Liberty ship that had a low carbon steel shell, and then the failure and a crack propagated around the entirety of the girth of the ship. And like I said, this is a low carbon steel example, which we'll see is particularly susceptible to failure as a function of temperature. Specifically, it'll go from a brittle fracture at low temperature to a ductile fracture at high temperature. And you can imagine if the ship set sail, say, from a warm water port, the steel might be in a ductile condition, and no, we don't want to. We want to keep, yeah, that's right, we don't want to see that again. Sorry about that. This ship sets sail from a warm water port. The girth is in a ductile condition, goes north and encounters very cold conditions. It becomes brittle, and the failure then ensues. So we'll look at that in great deal. The other example that I showed last time was that of the Aloha airliner, where the failure was the tearing off in flight of the canopy. In this case, it's an aluminum alloy. Where the failure occurred. And it occurred because of fatigue failure. This particular plane had many takeoffs and landings every day as it went from one Hawaiian island to the next. And so that the number of takeoff and landings exceeded the expected design number, and we saw a fatigue failure. But also corrosion was involved here because of the humid and alkaline conditions of the Hawaiian Islands. So it's kind of the perfect storm in terms of failure. But a lot of examples here that show different materials, different environmental conditions, sometimes wanted failure, but in most cases unwanted failure. So now we're going to start looking at different types of failure and trying to understand the mechanisms behind those failures. And then finally, we'll go on to start looking at some standardized test methods to help us include failure into the material selection process. So we're looking here at figure 8.1, and we're seeing two extreme cases of failed surfaces, both pulled in tension, or all three cases pulled in tension, and the failure surfaces all different. In one case, we've got what we'll call a ductile failure, and in this extreme right case, a brittle failure. And then the intermediate case between the two. So a few points about these failure mechanisms. One, they're very temperature and rate dependent. The ductile fracture occurs after extensive plastic deformation. The brittle case has little plastic deformation. Before fracture. So let's go back then and take a look at those. The ductile case, you can think of it as an example, perhaps like silly putty or even taffy, where it pulls apart with significant plastic deformation. The brittle case, though, you can see it's almost no plastic deformation. So that would be an example of that would be like a ceramic material, and the intermediate case might be a metal like aluminum alloy. Other characteristics of these surfaces are that the ductile type fracture is usually desirable from a use standpoint simply because the fracture might give an operator time to identify that the part is about to fail. But overall, we want to design to keep any plastic deformation from happening if at all possible. So here's that kind of that intermediate case between very ductile and very brittle failure. And we can see that we're basically, once again, loading a sample in tension. Initially, we see this neck forming, which is an indication of initial plastic deformation. And this is followed by microvoids within the metal. Microvoids forming within the metal. Of course, now we're peering in 3D. In most cases, those microvoids aren't apparent during processing. The microvoids will coalesce into an internal crack. And propagate until the edge and finally there'll be shear on the edges, which are an indication at that point of some preferred slip planes or slip system indicative of the metal. And this final failed surface is what's described as a cup and cone failure. And so that'll be the first quiz question that I'll ask on Monday. And that is, what is the name for the failure surface for a ductile metal such as aluminum? Excuse me. And the answer is a cup and cone failure I'll mark that Q1 so you know to be prepared for that answer. So one of the underlying mechanisms here in this sort of failed surface is that dislocations tend to pile up and act as barriers to form the microcracks. So down at the atomic level, we can trace those microcrack formation because of the entanglement and dislocations at the leading to the onset of the microcracks, and generally, under most conditions, those microcracks will form a macro crack, and then you'll get the classic cup and cone type failure surface. It's often indicative in the center region where it's fibrous in nature, which is an obvious ductile fracture surface. Where the brittle case is very smooth and non-fibrous. Surface, because you don't have those dislocation mechanisms acting like you do in the ductile case. So here's two samples showing these surfaces. This is an aluminum alloy, low carbon steel alloy. So clearly the metals can have both types of surfaces depending upon the alloy type as well as the experimental conditions. Both of these are macro images of, here's the cup and cone surface, and here's a brittle surface on the low carbon steel. So if we start peering down at the micro level, and this is figure 8.4 showing a ductile sample. At about 3,300 magnification here, 5,000 magnification on the right, and we start to see some rather unique features on these samples. This is the center in the center region that's fibrous. We typically see in ductile samples described as dimples, or kind of a cellular type structure in the center. And on the edges, where the shear failure occurs, we see those same dimples, but at a different angle because of the unique angular feature at the edges. And so let's go back and look at those. So here, this is where the dimples are coming from at high magnification, and this is the shear region at high magnification. So there's both macro images that we see appearing as well as micro images that we can attribute to ductile fracture surfaces. So let's go on and look at the brittle fracture examples. So here, fractures occurring with little plastic deformation, and it's most prevalent in metals with few slip systems, particularly hexagonal close-packed systems, zinc, magnesium, and recall the zinc single crystal case that we looked at earlier, as well as ceramics that have few slip systems and atom jump distances that are quite far compared to the metal case. So the cleavage is usually much smoother in ductile fracture and might be specific, for example, specific to certain planes. For example, that zinc case in the hexagonal close-packed plane where that was one of the designated slip systems that we saw. The other thing about brittle fractures is that often so-called chevrons mark the point of the crack origin. And so a chevron, trying to highlight the chevron there, a chevron there. So a chevron is a certain type feature that you can almost think about as a beak opening of a bird, perhaps. But the chevron on brittle fracture surfaces is almost it is often present and indicates where the brittle fracture occurred, and you can almost see lines pointing to this origin of the brittle fracture in these cases. So to summarize a little bit about brittle fracture, it occurs with little plastic deformation. Often a chevron with kind of the point of origin. And we'll see that the point of origin is typically a stress concentrator of some sort. Which probably makes sense given that initial example of the tablet, the pharmaceutic container, where we deliberately scored the sample and had a stress concentrator to open the package. In the brittle fracture, oftentimes there is a stress concentrator that begins the plastic deformation, and we can look for the chevron then and begin to understand maybe it was a poor design of the part, and there are ways we can address that we'll look at in subsequent lectures. So we can also look at the type of crack propagation within the microstructure, and we can define two types of crack propagation. The first is what we call transgranular crack propagation. So in this cartoon, it's supposed to represent a scanning electron microscope image showing the grain structure for a given metal alloy and how a crack is propagating. So the crack here is the dark red line. And in this example, it's trans or cutting through the grains, not following the grain boundary. So it's cutting indiscriminately across those grains in a transgranular fashion. And this is an actual micrograph showing a transgranular failed surface. Plastic deformation is apparent because we've got these smooth surfaces, which is an indication of brittle fracture. And also that we're cutting through the grains. It's a very smooth cut. In some cases, the grains have pulled out. From the microstructure, but in general, we've cut just indiscriminately across that surface, not following a grain, the grain boundaries. So transgranular then. Cuts across grains and has no apparent logical path. The second type is intergranular fracture. So once again, we're looking at a hypothetical scanning electron microscope. The grains are identified in the light brown. The crack is propagating, in this case, along the grain boundaries in a preferential manner. You can see that occurring here. Once again, it's still a brittle fracture, but now there's a preferred path along those grain boundaries. And in figure 8.7b, we see an example of a intergranular fracture. Try to identify that path for you here. You can see it actually is going maybe several paths along those grain boundaries, but definitely following the grain boundaries. We see still a smooth surface, but a preferred crack route. And this can occur for a number of reasons. So just noting that the intergranular crack propagation occurs along grain boundaries, but as I was saying, that this can occur for some distinct processing examples or reasons. One case that's been discussed in the literature is an aluminum alloy, where they found that lead precipitated along the grain boundaries. Creating a region of weakness or low strength. And in this case, it's purported that there was a Boy Scout troop that was collecting aluminum cans as a fundraiser, and they had loaded some lead shot in with their aluminum cans to increase the weight and value of the aluminum cans. Then that went to an aluminum smelter. They were remelted. The aluminum preferentially precipitated the grain boundaries, resulting in these intergranular failures. So depending upon processing, you can get either intergranular or transgranular fracture. In either case, it's a brittle fracture and generally unwanted, but those are two of the main mechanisms for failure, brittle failure, intergranular and transgranular fracture along the grain boundaries. So we're going to move on next to some actual testing procedures associated with failure. Here we're going to start with the Charpy impact test. It's used to measure a sample's toughness. The sample dimensions are shown here, where we take usually a metal sample and it's machined to ASTM standards. So this is one of the ASTM standard tests showing actually test E23, ASTM E23. It has the sample has specific dimensions, 10 millimeters by 10 millimeters, and there is a notch that is machined into the sample. That the notch is 2 millimeters deep and at a specific angle. You can see the loading conditions. The sample is laid horizontally or in a manner so that a hammer strikes the sample at the opposite side of the notch. The notch is a stress concentrator. Which ensures that the sample fractures at the notch then. There is a large testing apparatus shown here in figure 8.12, that includes a hammer that starts at a known height h. It swings through, hits our sample, and comes to some end of swing height. Getting really busy here, h prime. But if we know the original height, we know the final height, we can then back out the energy absorbed during this testing process. And this is called the Charpy impact test. There's a slight variant to the Charpy. It's called the IZOD test. Very similar, except here the sample is vertical and the notch is at the half support height here, and so it's just a different change in diameter. The Charpy test is the more common of the two. Just some notes then about the Charpy test. It is an ASTM standard. Test. It measures the energy absorbed during fracture. In units usually of foot-pound or joules. And this is an indication of the material's toughness. Now, this is the second indication of toughness that we've talked about. The first was looking at the stress-strain curve. The integrated area under that curve was also an indication of toughness. So there's two ways we can measure toughness. One, this integrated area under the stress-strain curve, or more commonly, this Charpy impact test. They might give slightly different values simply because the rates involved are much different. The Charpy test is a high rate, high strain rate. Whereas the stress strain curve would be a lower strain rate. So in terms of impact type failures, then in most cases the Charpy test would be more desirable because it's those high strain rates usually that result in impact failures. So let's take a look at the data that we get then. In this case, as a function of temperature. So we're plotting here impact energy versus temperature, and we begin to see that certain metals and in particular low strength steels have dramatically different behavior, where up here we'd say these are rather ductile materials that have high impact energy regardless of temperature. So they're pretty ductile. They can absorb a lot of energy upon impact. A lot of high strength materials would be more brittle. These might be ceramics. For example, under almost all temperatures, they tend to exhibit brittle type failure, low impact energy. But low strength steels, which are body-centered cubic, can exhibit both brittle and ductile temperature, or brittle and ductile failure, depending upon temperature. And so that's quite disconcerting, simply because you would like a material whose impact energy doesn't vary with temperature, but in this case the low carbon steel samples do. So let's just review a little bit. Some points to consider: that some materials have different impact energies with temperature. And face-centered cubic metals do not vary with temperature. So these variants are typically body-centered cubic metals. So we're going to trace this back to the slip mechanisms that are prevailing with these systems. Here's an example of low carbon steels, a variety of low carbon steels showing impact energy with temperature. The value here that's shown is the weight percent carbon in the steel sample. And so as we get to these lower values, 0.01, 0.11, we're getting less and less carbon. And as we get very, very low, then this would be 99.99% iron, almost pure iron. And we see as we increase the percent carbon, there's a shift downward. But for these real low carbon steel samples, there is a distinct change that results very brittle at low temperatures and very ductile at higher temperatures. And this is less pronounced as the percent carbon goes up. But we'll see that even with some of these higher carbon samples, that at room temperature, for example, there's a dramatic change in some of them, and very dramatic with the ones that have the lowest percent carbon. We call this phenomenon the ductile to brittle transition temperature. So in the extreme case, we'd say that the ductile to brittle transition temperature is here. Where it's essentially an S-type curve. And you can imagine for design purposes, this is very important that you understand, especially for those low carbon steels. So it's a well-defined a value for many body-centered cubic systems. Particular things like ocean liners, ocean liner materials. Recall that hull of the boat that fractured. That was because of a lack of understanding of the ductile to brittle transition temperature of a low carbon steel, and just automotive parts. Those that might be subjected to both high temperature and low temperature and see some impact, like rims and tire rims, for example. Fortunately, this phenomenon is unique to low carbon steels, and we can tie it back to it's a rate phenomenon. That's unique to body-centered cubic metals, and it's found that as temperature increases, crack growth decreases, and dislocation movement increases. Apologize, that's some crazy writing there, but the important point is that we can relate this back to dislocation movement as a function of temperature for these body-centered cubic systems, in particular low carbon steel. Fortunately, we have an understanding today about this phenomenon, and it allows us then to choose materials selectively to avoid this sort of ductile to brittle transition temperature. So the quiz question 2 will be to give the phenomenon with low carbon steels and impact energy as a function of temperature. And the answer is the ductile to brittle transition temperature. So quiz question 2 is, what is the phenomenon of impact energy versus temperature for low carbon steels? And the answer is the ductile to brittle transition temperature. But fortunately for most materials, face-centered cubic metals, ceramics, HCP metals, we don't see this dramatic change in temperature or impact energy with temperature. We're looking here at a series of low carbon steel sample Sharpie impact samples. Obviously, a macro view of those. And we're looking at the Sharpie samples as a function of temperature. Testing temperature. So this might be almost getting to boiling water, high temperature. This might be down in the liquid nitrogen range. And of course, room temperature, assuming degree C here. But what we see is that at the low temperature, these samples are brittle, giving our classic smooth surface, and then they become more ductile here as that temperature increases. In all cases, the fracture occurred here at this notched surface, which is expected and desirable in the Sharpie impact test. So once again, that S-shaped curve that's common for low carbon steel samples. And this is a classic question, once again, on the FE test or the professional engineering test. Name the phenomenon of transition from impact as a function of impact energy versus temperature, and that being the ductile to brittle transition temperature, and this is common for low carbon steels. Next, we're going to begin to to investigate a somewhat similar phenomenon that involves fracture toughness. Once again, bringing into the concept of toughness, but we'll see it's a little bit different than the previous examples of toughness that we've looked at from the stress strain curve and the Charpy impact test. We identify two types of cracks here that might exist. One is an internal crack, and the other is an edge crack. And both of these could be common in a sample. An edge crack, for example, could form by a sharp surface object. An internal crack could occur simply during processing, say rolling or forging. Those sort of metalworking operations might give you an internal crack. Much more difficult to identify, obviously, because you can't peer inside the metal, whereas the edge crack is more obvious. And so we'll take up, when I return on Monday, we'll start looking at fracture toughness testing, where we'll load the sample in tension as we've done before, but we'll see the effect of both the edge as well as the internal cracks. So just to review a little bit, identify these quiz questions. Quiz question 2 involves the ductile to brittle transition temperature. And quiz question 1, the type of fracture surface that's typical of a ductile tensile test sample, and that is the cup and cone fractured surface. So that's the answer to quiz question number 1. And with that, we'll stop the lecture, and I look forward to seeing everybody in class on Monday. And don't forget that next homework set over chapters 6 and 7 is due on Monday.